Hello guys, welcome back to the universe of Tekam. In this tutorial, we will learn about Prim's algorithm. This is the minimum spanning tree algorithm. It is a greedy algorithm used to find the minimum spanning tree of a weighted graph. It starts with an arbitrary vertex and repeatedly adds the smallest edge that connects to a vertex in the minimum spanning tree to a vertex outside of the minimum spanning tree until all vertices are included. Prim's algorithm is a greedy algorithm used to find the minimum spanning tree of a connected undirected graph. A spanning tree is a subgraph that includes all the vertices of the graph and is a tree, while the minimum spanning tree minimizes the sum of the edge weights. The key features of Prim's algorithm is that it gradually grows the minimum spanning tree by selecting the smallest edge that connects the tree to a vertex outside the vertex. This is what is Prim's algorithm. Next, we need to know about why Prim's algorithm we use it. We need to find the minimum spanning tree. So that is what we need to use the minimum spanning tree. Prim, so that is the reason we need to use Prim's. And Prim's algorithm used to find the minimum spanning tree of a graph, which is useful in various applications where we want to connect all the points nodes with the least total cost weight. It is particularly efficient for dense graph where the number of edges is high compared to the number of vertices. Next, Next, applications of Prim's algorithm. The applications we are used in network design, designing a least cost network such as telecommunication or computer network. This is the application and minimum cost wiring, connecting a set of points like houses with the least amount of wiring like that. And another one is cluster analysis. In data analysis to connect a points in a way that minimizes the total distances. The next one is graphics and geometrics algorithm. Geographical mapping connecting a points of a interest in a geographical area with the least cost. This is all about applications of Prim's algorithm. Next we move on to the algorithm steps. First step is the initialization. Initialize a start with an arbitrary vertex and mark it as part of the minimum spanning tree. Initialize a priority queue, minimum heap to store the edges. The next one is start with an arbitrary node, say A. Add the node to the minimum spanning tree and mark it as visited. Create a list or priority queue to hold the edges that connect the minimum spanning tree to vertices not yet included. Next one is for each neighboring node of the current node, add edges to the queue. While the queue is not empty, remove the edges with the minimum weight from the queue. If the vertex is not in the minimum spanning tree, add it to the minimum spanning tree and mark it as visited. This is all about growing of minimum spanning tree. Next, add all the edges connecting to a new node to unvisited nodes to the queue. Repeat until all the vertices are included in the minimum spanning tree. The algorithm terminates when all the vertices are included in the minimum spanning tree. This is the what Prim's algorithm says. We take one example to how Prim's algorithm works. I take one graph. This is the graph I take. First steps to apply Prim's algorithm is select any vertex as the starting point. Let's start with A and maintain two sets. First one is minimum spanning tree. Vertex is included in the minimum spanning tree. The next one is non-MST set. That is not yet included in the minimum spanning tree. We keep track of the minimum weight edge connecting the minimum spanning tree set to the non-minimum spanning tree set. First step is start with the vertex A. The minimum spanning set is A. The edges are connected to A is A to B. Edges are connected with A to B. The weight is 1. The weight is 1 and A to C. The weight is 4. Choose this edge. Which one is small? A to B is the smallest. The weight is 1. Add B to the minimum spanning tree set. Add MST. Minimum that is A to B. The weight is 1. Right. Next step is expand the minimum spanning tree to include B. Step 2. The step 2, what it says? The MST set is minimum spanning tree. Right. A comma B. Comma B. That is A to C, and the non-MST is A to C. I need to take non-MST A to C, the weight, and B to C and B to D. Right. B neighbors are the B to C and B to D. The weight is B to D weight is 2 and B to C weight is 3 and A to C weight is 4. Next, choose the smallest edge. B to D is the smallest, right? The MSTs, add the MST set. Add MST set. B to D to the MST set. That is B to D is MST. The weight is 2. 2. Next, this is the step 1. Step 3, expand the MST set to include D. Include D. This is include A. Include A. This is include B. Include B. Include D. The MST set is A, comma B, comma D. The edges connected to D is non-MST set in previous is A to C. The weight is 4. Next, B to C. The weight is 3. In D neighbors are C to D and D to E. C to D. The weight is 5. And D to E is weight is 7. Choose the smallest edge. Which one is smallest? B to C is the smallest. Add C to the MST. MST set, that is B to C. B to C is equals to 3. Next step is expand the minimum spanning tree to include the C. In step 4, include the MST set is A, comma B, comma C, comma D. A, B, D, then C, right? Now correct. The edge is connected to ABCD in previous. We now need to choose the minimum weight edge that connects any vertex in the minimum spanning tree set to a vertex outside the minimum spanning tree set. Consider A to C. The weight is 4. The vertex C is not yet in the minimum spanning tree set, so this edge is valid. They consider B to C. The weight is equals to 3. The vertex C is not yet in the minimum spanning tree set. This is smaller than A to C. Next one is other edge. The C to D is ignored as both C and D are already in the minimum spanning set. So C to E is weight is equal to 6. The vertex E is not yet in the minimum spanning C set but is larger than B to C. Next one is D to E. The weight is equal to 7. The vertex 7 is not yet in the minimum spanning tree. set but is larger than B to C. The smallest edge among those considered as B to C weight is equal to 3. Update the minimum spanning tree. Add the edges B to C and to the minimum spanning tree. Add the vertex C to the minimum spanning tree. Update the minimum spanning tree A, B, D, C. All the vertices include the minimum spanning tree is A, B, D, C, E. All the vertices are now included and the algorithm is terminates. And finally, we need the edge connected to A, B, C, D is C is connects to E. The C to A weight is 6. Then D to E. This weight is 7. Choose the smallest edges at E to the minimum spanning tree. C to A E is the weight is 6. So this is the smallest at the beginning of the step 4. Vertices included in the minimum spanning tree. Set A, B, D, C. Final resulting a minimum spanning tree A to B is resulting minimum spanning. One is A to B. Here the weight is 1 and B to D. The weight is 2. B to C. The weight is 3. Next, C to E. The weight is 6. This is the final. The total weight of minimum spanning tree is the MST. Total MST is the total MST is equals to 1 plus 2 plus 3, 1 plus 2 plus 3 plus 6 is equals to 12. This is the total minimum spanning tree of the Prim's algorithm. Next, we move on to the Python code implementation. First, I need to import HippyQ. The purpose of line import CPQ model, which provides an implementation of the minimum heap. A minimum heap is a property, a queue where the smallest element can be accessed in the constant time. This is crucial for Prim's algorithm. As well, need to repeatedly extract the minimum weight edge from the graph. So that's why we need to import HippyQ. Next, define Prim graph, comma, start. This defines the function Prim, which takes two arguments. Graph, a dictionary represents the graph. Each key is in a node and each value is a list of tuples, where each tuple is representing an adjacent node and the weight of the edge connecting them. And the starting node of the Prim's algorithm from which will be constructing the minimum spanning tree. Next, we need to construct minimum spanning tree is equals to store the edge of the minimum spanning tree. That is why I need to initialize an empty list minimum spanning tree. Next, visited set to track the visited node. So that is we need to initialize an empty set visited. This set will be used to keep track of the nodes that have already been included in the minimum spanning tree. Next, we need to store the initializers and minimum heap. So the minimum heap 0 comma start. Minimum heap to store the edges. The purpose of minimum heap is priority queue. Minimum heap with a tuple start. The first element of the tuple 0 is the weight for the starting node. The second element is starting node itself. The minimum heap will be used to extract the edge with the minimum weight that connects a node inside the minimum spanning tree to a node outside the minimum spanning tree. Next, we need to using while edge, while minimum heap, while minimum heap. This starts a while loop that continues as long as there are edges in the minimum heap. As long as there are edges left to process, we keep extracting the minimum weight edge and adding in new nodes to the minimum spanning tree. The weight equals to the weight comma vertex is equals to heap eq dot heap heap of minimum heap get the minimum edge. This line extracts the smallest edge from the minimum heap using a heap dot heap of result in a tuple weight vertex. The weight is the weight of edge. The vertex is the node connected by the edge. The edge with the minimum weight is removed from the heap and we proceed it next. Next, we write if vertex not in visited, if vertex not in visited, this condition checks if the vertex has already been included in the MST. If the vertex is not yet in the visited set, we process it to add it to the minimum spanning tree and update the minimum spanning tree state. Next, the visited dot add. The visited dot add vertex, comma, weight. Add the vertex to the minimum spanning tree. Adds the current vertex to the minimum spanning tree list along with the weight of the edge that connects it to the minimum spanning tree. This is done to the record vertices the and edges that are part of the minimum spanning tree. Next one is for neighbor comma edge weight graph into what? Next, if neighbor not in heap eq, heap push minimum heap edge weight neighbor. This for loop iterates over all the neighbors of the current vertex and adds them to the minimum heap. Next, the graph vertex gives a list of tuples representing the neighbors of the vertex and the weight of the edges connecting them. For each neighbor, the neighbor comma edge weight, the algorithm checks if the neighbor has already been added to the minimum spanning tree, whether it's in the visited set. If the neighbor has not been visited, it is added to the minimum heap as a potential edge to add to the minimum spanning tree with its edge weight. Next, return the minimum spanning tree. Return the first element 0 comma start is not a part of the minimum spanning tree, so return the rest. So that way we need to use a return statement. After the loop finishes, the algorithm returns the minimum spanning tree list excluding the first element. This reason exclude the first element is that the starting node does not have an edge associated with it. Next, we need to represent graph. Graph. This is the representation of the graph where each key in the dictionary represents a node. Each value is a list of tuples where each tuple represents a neighboring node and the weight of the edge connecting the nodes. Next, calling the prim function. Minimum spanning tree MST equals to prim graph comma a. This calls the prim function, passing the graph and specifying that node A is the starting point of the algorithm. Next, print the minimum spanning tree. Minimum spanning tree for vertex weight. Print vertex, the vertex comma weight. This prints the vertices and edges of the minimum spanning tree. Each edge added to the minimum spanning tree is displayed with the corresponding vertex or neighbor vertex and edge weight. This is all about Prim's algorithm. The summary of the process is, first we need to initialize the priority queue. Minimum heap is used to store the edges by their weights. The starting node is added to the minimum spanning tree. Next iteration, the algorithm iteratively select the edge with the smallest weight that connects a visited node to an unvisited node and adds it to the minimum spanning tree. The neighboring nodes of the newly added node are pushed into the heap. Next, the process continues until all the nodes are visited, at which point the minimum spanning tree is fully constructed. This is all about how Prim's work, Prim's algorithm works. Then we need to run this code. I need to run this code. The output of Prim's algorithm, the minimum spanning tree is vertex B weight 2, vertex C weight 3, the vertex D weight 4. This is the minimum spanning tree Prim's algorithm. If you like this video, please don't forget to subscribe, like and share and comment in this video.